Okay, welcome back. So let's have a quick look at the data that was recorded by the machine vision program that was designed in LabVIEW. As we saw in the previous video, we were able to set up a simple trial, try to eliminate as much background noise as possible, select an optimal match score, and go ahead and roll an object that was being tracked, and we would start and stop the tracking as close as possible, if not exactly at the same time that physical timing or real timing using a stopwatch of the object moving from initial starting point to final endpoint at a predetermined distance. So we've gone ahead and taken a second trial, a much cleaner trial, and this is the result. I was able to basically start the trial at the exact same time the real world stopwatch was pressed, and so they both simultaneously started recording time and data, and we were able to stop recording time and data simultaneously as well. And what we did do was allow for a small amount of time to let the program recognize and draw the bounding box around the object of interest, and then we gave it a slight push and allowed it to roll a new distance, 440 millimeters, and it rolled along this distance for 2.39 seconds. And as you can see, several snapshots were taken as indicated in highlighted blue, and a small analysis was conducted just to see how accurate is this machine vision, and was it very far off in the end. And the results were surprising. They were actually quite close to the real world results, or the theoretical results. The experimental results were very close actually. So what we ended up realizing was that if you have a look, there were slight changes in the X and the Y direction, X being the left hand side column and Y being the right, and all values before, as already previously stated, were actually just so that we had given some time for the software to recognize the object. And so we went ahead and we did the trial. We can see down here we had around 2, 4, 6. So we had 6 frames and around about 3 seconds, 2.39. So it was roughly about 2 frames per second, roughly about 2 frames per second. So that was actually slightly more. It was almost 2.5 frames per second. But since we're dealing with a single discrete snapshot, it is a whole number, so about 2 frames, 2 to 3 frames per second for the duration of the trial, of course. Yeah, and if we go ahead and we have a little bit of a look at the physical measurements that we did have, we already specified that it was 440 millimeters and the trial was for 2.39 seconds. And in the X direction, it traveled a machine vision distance of 772.9 pixels, and in the Y direction 10. And this disparity, and the reason why it traveled in the Y, was it was rolling at a slight angle due to the actual table being at a slight angle, as well as even the camera not being perfectly leveled, and this has contributed to values being recorded in the Y direction. We go ahead and we do some mathematics, and we analyze that it's approximately 1756 pixels in the X direction and 23 pixels in the Y direction per meter. So that's what's going on right there. And we've decided to neglect the Y value because the X values are much greater than the Y. So it is a condition that we've decided to go ahead and use. It is assuming the Y values minimal effect, and just using some simple kinematics to analyze the velocity of the object. Theoretically, it's moving at about 184 millimeters per second, which is quite slow. You know, it's about it's a very slow and steady distance about. And if we go ahead and we have a look at the pixels divided by 2.39 seconds, it equates to about 266.54 pixels per second. And now what we want to do is we want to take the total amount of pixels that it has traveled and divide it by this 266 pixels per second, and the time we end up getting is 2.9 seconds. So according to the distance traveled by the object and machine vision, it believes that it has traveled for a time of 2.9 seconds. Now, obviously, due to latency of the machine vision taking snapshots as opposed to continuous timing, and it's drawn a bounding box around. So it is tracking it effectively, but it's not taking enough snapshots to track it as we have in real life. So it's doing a very good job for its latency, for its limitations, but the error is still quite significant. In fact, if we were to just go ahead and calculate that error, so we came down to the conclusion that if it did travel, according to the machine vision, because it did travel 2.9, it took 2.9 seconds to travel a distance of 440 millimeters, it was traveling at a different velocity to the theoretical velocity, and this experimental value has turned out to be 151.7 millimeters per second. And if we were to go ahead and just determine the percentage difference between these values, so 184, so there is an error of about 18%. There's an 82% similarity, but there is an error, there is a disparity there, and we've just been able to calculate that. Now, using this data, we have physically sat down here and calculated this in a very short space of time. This will obviously and can be done at much greater speed and can actually be used to increase the tracking ability of machine vision that has been attached as a module to a PLC, and it will allow itself to correct itself. And this is effectively a control system, and this is a prime example of how we can analyze the data, but this data can also be analyzed in the computer by the PLC, and it can correct itself and become much more accurate, and its sensing can, as a result, be far more accurate and effective.